So up to this point, we've used matrices, more notably augmented matrices, to help us solve systems of equations. Let's talk more about what a matrix is and some features about matrices. A matrix is an ordered rectangular array of numbers. A matrix with m rows and n columns has size m by n, so it's number of rows by number of columns. An entry in the ith row and jth column is denoted by little a, I of j. So capital letters are usually used to designate a matrix. Lowercase letters with subscripts are used to indicate specific elements that are in that matrix. The size or dimension of a matrix is described in terms of number of rows and columns. A matrix of size 1 by n having 1 row or n columns is referred to a row matrix or row vector of dimension n. And of course, there's also a column matrix, which basically has m number of rows but only one column. If the number of rows and number of columns are the same, we call it a square matrix, which I used a number of times in the previous video, but didn't explain what it was, but that's what it is. Equality of matrices. Two matrices are equal if they have the same size and their corresponding entries are equal. Addition and subtraction of matrices. If A and B are two matrices of the same size, so they have to have the same dimensions, then I can add them together or I can subtract them. If they're not the same dimensions, I can't do that. Scalar product means that if I take a constant and multiply it to a matrix, everything in the matrix, every element of the matrix gets multiplied by that constant. So for example 1, let's answer these questions for me. What is the size or dimension of matrix A? How about matrix B? How about matrix C? What about matrix D? The sizes shouldn't be all that difficult for you to come up with. I can see here I have 3 rows. This is a row, this is a row, this is a row, so 3 by column, column, column. So it's 3 by 2. And I can see B has the same number of rows and columns, so it's also 3 by 2. C, I have 1 row, 2 rows, 3 rows, so 3 by 1 row, 2 rows, 3 rows, 3 columns. So it's a 3 by 3 matrix, square matrix, and so is D. There's a plus sign missing here. Let me put it in there really quick. It's asking you a question here. Why doesn't this matrix A plus C not exist? So in your own words, explain why A plus C does not exist. Well, remember, for me to add two matrices together, or subtract them for that matter, they have to have the same number of matrices. Now I'm saying inner dimensions here. The dimensions are not equal. So with that being the case, I cannot add the two matrices together. And I was doing multiplication there when I made this, but it should just be A plus C, so don't mind that. So now compute A minus B. Well, I could see here that, again, A was a 3 by 2 matrix, and so was B. They're the same size, so I should be able to do that. So take a moment and let me know what this should be. Okay. The only thing you have to kind of be wary about is make sure that you're distributing properly. If I'm going to be doing, A minus B, that means that each term, like this minus this, so -1 minus 2 would be one of them. So if I had those two matrices being subtracted, then, I'm going to have -1 minus 2, 3 minus 3, 4 minus -2 in the first column, 2 minus 4, -2 minus 1, 0 minus 2 in the second column. And if I simplify all those, this is the matrix I get. When I do like adding and subtracting constant multiples of matrices, I have to make sure I am following the order of operations as well. So take a moment and compute what 2a minus 3b would be. Well, to work this out, I have 2 times that matrix, -2, -1, 3, 4, 2, -2, 0, when I read across the columns. 3, 2, 3, -2, 4, 1, 2, reading across the columns, being multiplied by 3, and then I'm subtracting. So if I do the scalar multiplications, the first matrix has columns -2, 6, 8, and 4, -4, 0. The second one, as you see here, what you're seeing here is I distributed the -3, so that's why there's a plus out here now. But all the numbers inside the matrix got multiplied by -3, so I have -6, -9, 6, and -12, -3, 6 in the columns. And when I add them together, -2 plus -6, 6 plus -9, etc., etc. Numbers in the same positions all across the board. And so when I get my final answer, the first column would read -8, -3, 14 from top to bottom, and the second column would read -8, -7, -6, going from top to bottom as well. Laws for matrix addition. Matrix addition, it's commutative, so it doesn't matter which order you add them. And same thing with associative. It doesn't matter which order. If you have 3 or more matrices, it doesn't matter which order you add them together. Transposition of a matrix. Although they don't have you do a whole lot with being able to transpose a matrix, transposing a matrix basically means taking a matrix that's m by n and making it n by m, which means you're basically interchanging the rows and the columns. So for instance, if I'm looking at this is a 2 by 3 matrix, or 2 by 4 matrix, sorry. If I transpose it, I should end up with a 4 by 2 matrix. So, with that in mind, tell me what the new matrix would look like once it's transposed. Okay, so if I let this matrix be, say, matrix A, then A superscript T, well, I didn't finish writing it, then A superscript T, well, row 1 is going to become column 1, so it's now going to be 4, 2, 0, -1, and row 2 is now going to become column 2, 3, 4, -1, 5. Now, there are reasons to transpose a matrix. There's specific calculations to do them with. Some of it depends on what the rows and columns represent and whether or not you need to change that around to fit a given situation. But there's other specific calculations that this course is really not going to get into doing, for the transposition. That's just something that they want you to be able to do and know what it looks like if you need to transpose a matrix. So, I'm not going to spend too much time on transposition as it is. Multiplication of matrices. So, we talked about addition, subtraction, scalar products. But what if I multiply 2 different matrices? It could be done as long as, you're told that A is an M by N matrix, and B is a P by Q. The first thing is, for me to be able to do multiplication, this dimension and this dimension have to be the same. We often refer to those as inner dimensions. Which means when I write them in order, if I do A times B, and I say, okay, this is M by N, and this is P by Q, these are the inner dimensions. As long as they're the same, I can multiply them, so the multiplication would exist, and the resulting matrix would be an M by Q. I would use the outer dimensions to figure out what the final answer's dimensions are going to be. Knowing how the structure is going to look is going to become very important, as well as knowing whether or not you can actually multiply the matrices through. So I don't have to have the same dimensions to multiply matrices. As a matter of fact, there are some that if I have the same dimensions, I wouldn't be able to multiply them at all. It's just that I need to make sure that I have the same number of columns in the first matrix being mentioned in the product as I have rows in the second. So, for instance, going back to some of the examples we saw before, these are the same matrices we had in previous examples. Determine the following if possible. So I look at A and B. A and B are both 3 by 2 matrices. Since these dimensions are not the same, it's not possible. B times C. B is a 3 by 2. C is a 3 by 3. Again, these inner dimensions are not the same. It's not possible. C times B, on the other hand, well, if I look at it, these two are the same. I can carry through that multiplication. How do you do it? And this is where it gets tricky. When I multiply, when I put them in the same order, when I do, C times B, I'm going to start with this, and I'm going to basically take this row and multiply it to this column. So basically this one and this one get multiplied, this one and this one get multiplied, this one, the triangle, and this one get multiplied. And that's going to make up, one term. So I would take 3 times 2 plus negative 1 times 3 times, kind of obscured it here. I forgot what number that is. 0 times negative 2. And I would add those all together, and that would give me my very first term in row 1, column 1. And then I would do the same thing, except I would now go to column 2. So row 1, column 2, I would do the same thing. These two would be multiplied, those would be multiplied, those would be multiplied, so forth and so on. So if I carry that through, you're going to see 3 times 2 plus negative 1 times 3 plus 0 times negative 2. In the second column, you're going to have 3 times 4 plus negative 1 times 1 plus 0 times 2, so forth and so on all the way down. I know this should end up being a 3 by 2 matrix because that's what the outer dimensions are. And I would carry through the same kind of procedure again and again and again. And I would end up with this product here. C times D. C is a 3 by 3 matrix. D is a 3 by 3 matrix. These are the same. So I can multiply them. So again, I'm going to take, 3 times 2, 3 times, or negative 1 times 3, 0 times negative 2. Oh, that should be a square. That should be the triangle. And I go through the same procedure. I take each row of the first matrix and multiply it through the columns of each of the others and adding the results together. And that's going to give me each term of the matrix. So I don't show all the work here because I didn't have a whole lot of room, but that's what you would get if you would do all that work. So like 3 times 2 plus negative 1 times 3 plus 0 times negative 2 is just 3. This one right here. And you have to do that for each of the other 9, or the remaining 8 elements of that matrix. So it could be a little on the tedious side if you do this. Laws of matrix multiplication. Multiplication is associative. We saw, and basically we see here in B and C, that it's not commutative. I can't reverse multiplications of matrices. It is associative, so if A times B times C exists, then I could do A times, or I could do B times C, and then do A times that result. I could also distribute. An identity matrix, you notice it's kind of the same description as we had for, reduced row echelon. So it's an identity matrix. Basically, it's like if I took a matrix times an identity matrix, and it could be done, the inner dimensions work out, then basically this is like having a 1 for numbers. Any matrix times an identity matrix that would actually work with that number is just going to give you back the original matrix. So for this example here, there are 3 network consultants, Alan, Maria, and Stephen. Each received a year-end bonus of $10,000, and they decided to invest in a 401k retirement plan sponsored by their employer. Under this plan, each employee is allowed to place their investments in 3 funds. Those funds are an equity index fund, I, a growth fund, II, and a global equity fund, III. The allocations of these investments in dollars are of the 3 types at the beginning of the year are summarized in the matrix. So basically, it's telling you that Alan is putting 4,000 into an equity index fund, 3,000 into the growth fund, and 3,000 into the global equity fund. And then it's very similar for Maria and Stephen. Notice that these rows, or these column headings and these row headings, are the same thing, because these are the interest rates or return rates for those 3 accounts. So it stands to reason, if I want to figure out how much of a return each one got, then I'm going to want to take the $4,000 from Alan into the first investment option and multiply that by 0.18 to get how much he got as a return. And then 3,000 times the 0.24, and then the other 3,000 times the 0.12, and carry that through to get how much Alan earned as far as return investment goes. Same thing with Maria and Steven. So I want to multiply these 2 matrices essentially. I just have to make sure they're done in the right way. Okay, I mean, this is a 3 by 3 matrix. This is a 3 by 1. If I did B then A, then I would have 3 by 1, 3 by 3. Oh, can't do it. If I do A times B though, 3 by 3, 3 by 1, we're all good. So that's the first thing. And also, I mean, I should have, between the 2 pieces of data, I should have a matchup between the column headings of one and the row headings of another. If that's not happening, then it's like, well, should you really be multiplying those 2 matrices together? Because what does it really represent? But anyway, here it's going to tell me how much money was, additional that these 3 earned from various interests and things like that by their investing into these accounts. So I'm going to clear this up a little bit. Let's do this real quick. All right. So if I do A times B, I know I'm going to be able to do it, and I'm going to have a 3 by 1 matrix when I'm done. And that basically that final matrix will look like it'll have row headings of Alan, Maria, and Steven. It's only going to have one column, which is going to be the amount of money that was returned to them, like interest. That's basically what it is. So A times B, you can see I worked it out using the procedure we talked about before. And I got 1,800, 1,920, 1,680, which again, those represent the amounts that, this is Alan. This is Alan, Maria, Stephen. So basically, the person that had the best return was Maria. She got an additional $1,120 from investing her bonus in the funds that she did and the way she did it. And you had Steven, who had the worst because he earned the least from that. Inverses of matrices. Inverses of matrices, obviously there has to be a way to get to an identity matrix, and also the inverse of a matrix can be used to help solve equations as well, or systems of equations. So that's what we're going to be looking into and kind of going with on this one. So the inverse of a matrix basically is a square matrix of size n, such that if I multiply that to some other original matrix, I would end up with some sort of identity matrix. So find the inverse of a matrix. What you basically are going to do is you're going to kind of do a different type of augmented matrix. You're going to augment the original matrix you have. It should be a square matrix because only square matrices can have an inverse. So I would take that square matrix and have that on the left, and I would augment the proper identity matrix to the right of it. And then you would perform your row operations until the left-hand side becomes the identity matrix or the reduced row echelon form, what have you. And then what's on the right should be the inverse of that matrix at that point. So let's have a look and see how we would go through and do this. So we have these two matrices, and we want to be able to find the inverses of them. Now, both of them theoretically should be able to have an inverse because they are 3 by 3. That's not the only requirement now. You could have a 3 by 3 or a 2 by 2 matrix. They're both square matrices. I said they were both 3 by 3. They're both square matrices. But just because they're a square matrix doesn't mean it's going to have an inverse. Okay? It just means it can. Whereas if it's not a square matrix, there is no way, shape, and form that there's going to be, quote unquote, an inverse of that matrix that I can multiply to it to make it an identity matrix. This won't happen. So, take a moment with that idea and determine what the inverse of the matrix you see in A would be. As it stated on the previous slide, if I want to find the inverse of matrix 2, 3, 3, 5, I'm going to take that matrix and I'm going to augment it with the 2 by 2 identity matrix. And what I want to do is perform row operations that's going to make the left-hand side, the one that's on the left of the vertical line, into the identity matrix, and then the matrix I have on the right should be the inverse. So, much like before, I have a 2 here. I would like it to be a 1, so I'm going to basically divide row 1 by 2, or multiply by a half. And so these become 3 halves, 1 half, and remain 0 specifically. I established the 1, which means now the 3 that's down here needs to become the 0. So I am going to take row 2, and I'm going to subtract away 3 times row 1. And that's going to put the 0 down there 5 minus 3 times 3 halves is going to be 1 half. 0 minus 3 times 1 half is a negative 3 halves. And 1 minus 3 times 0 is still going to be 1. So far, so good. So I now have this column established. Anything I do beyond this, that column should remain unaltered. So I'm going to do I'm going to do 2 times row 2 because I want this to become a 1, which it does. And then if I do negative 3 halves times 2, I get negative 3, and 1 times 2, I get 2. The last thing I have to do now is get this to be a 0. So I'm going to take row 1 and subtract away 3 halves times row 2. 1 minus 3 halves times 0 is 0. So again, this has remained unchanged. Let's see. 0, or 3 halves minus 3 halves times 1 gives me the 3 halves minus 3 halves, which is 0, which is what I wanted. 1 half minus 3 halves times negative 3 does give me 5. And 0 minus 3 halves times 2 gives me a negative 3. So this is what I end up with on the right when I carry through the row operations for this special augmented matrix, which means that is the inverse matrix of 5, negative 3, negative 3, 2, reading down the columns. For this one here, take a moment and see if you can find the inverse of this matrix. Okay, same general procedure. I'm going to write it as an augmented matrix. I notice that in the upper left-hand corner I already have a 1, so that's pretty easily. I just have to get, this 2 here and this 2 here to become zeros. So I'm going to take row 2 and subtract away 2 times row 1. I'm going to take row 3 and add 2 times row 1 to get the new row 3. Row operations for this steps are going to be row 2 minus 2 times row 1 and row 3 plus 2 times row 1. And if I carry them through, I get I get the zeros where I want them on the left hand side here. And then each of the other cases, like for instance 1 minus 2 times negative 1 gives me 3. 2 minus 2 times 3 gives me negative 4. So forth and so on. I'm not going to go through each of those. You'd have to carry through each one of those calculations, but that's what you would get. And so, again, if I'm careful about how I do this now, this column, which now has the 1 and zeros where I like them to be, should stay that way. Next thing that has to change is I want this to become a 1. So I'm going to take row 2, and I'm going to multiply it by a third, divide by 3, whichever way you want to put it. And if I take the entire row and essentially divide it by 3, that's what I get with row 1 and row 3 being unaffected. Now that I have the 1 right here, this and this need to become zeros. So if I take row 1 and add row 2 to it, that would just make, the numbers in those positions, the negative 1 become a 0. And likewise, if I want to take negative 4, I'm going to add it to 4 times row 2, and that should make that one a 0. So the row operations are, I'm going to take row 1 and add row 2, and I'm going to take row 3 and add 4 times row 2 to it, and that's the result I get. So I have the ones and zeros where they all need to be in the first two columns. And again, if I keep continuing this the right way, that those are not going to change anymore. This should remain static for the rest of this problem. I now want to make the 8/3 in the bottom right hand corner on the left side into a 1. So I'm going to multiply row 3 by 3/8. And as far as the rest of it goes, 2/3 times 3/8 is 1/4. 4/3 times 3/8 is 1/2, and 1 times 3/8 is 3/8. Now I just got to get these two numbers here and here to become zeros. So I'm going to subtract 5/3 times row 3 from row 1, and I'm going to take row 2 and add 4/3 times row 3 to it, so I could get the zeros and ones all lined up where they're supposed to be on the left and finish that part off. And when I do that, the top row becomes 3/4, -1/2, -5/8. The middle row becomes -1, 1, 1/2. The bottom row, of course, had finished in a previous step or two. So that would be the inverse of the matrix. The inverse of this matrix would be this matrix right here. I'm not going to read it all. You can see it, but that's how you would have to write it. Inverses of matrices is an idea of this. They give you some formulas here that you can actually do for a 2x2 matrix. There is a shortcut formula. They talk about the determinant, which is something we haven't talked a whole lot about, and they don't talk much about it in the textbook either. And the last thing they're talking about here is being able to use inverses to solve a system of equations, because essentially, if you have something of this format here, where A represents all the coefficients in your system of equations, X represents all the variables in the system of equations, and B is basically a representation of the right-hand side of each equation, then if you do A inverse times that B, you should get back what X, Y, Z, whatever the letters are there, all equal. So for instance, I want you to solve this system of equations. I'm going to show you how to do it using the previous idea and the calculator to a certain extent, because the calculator can help you do it, and although I'm not going to show much with the calculator, but I want you to figure out what x1, x2, and x3 are for this circumstance, and then I will go through this one. So for this one here, I have three variables, x1, x2, and x3. That's going to be my X matrix. This one here. The right-hand side is this is my right-hand side matrix. And all the coefficients I have, this is my x1 column, this is my x2 column, this is my x3 column. Those are the coefficients that go in those positions. So I know that if I were to take A times X, I should get an expression that equals B. I'm not doing it that way, though. What I'm going to do is say, well, if that's the case, that means that X, those values there, should be the same as me doing A inverse times B. So if I could find if I could find an inverse of the matrix A and multiply that to B, then that's going to give me my solution. So I did this. I'm not showing all the inverse calculations or anything, because we just talked about how to do that, and so you should try to do that on your own. And if I do that, these are the answers I get as decimals there. And so my solutions are x1 being -3, x2 being 2.8, and x3 being 2.6. That's all I have. If you have any further questions with any of these, please let me know and please bring them up in class. However, until the next time, I will see you around. Have a good day.